Now let's see what if there are multiple cash flows involved. Depend on whether those multiple cash flows are equal in amount or not. We have two types. If they have equal amount, we call them annuities, and if they are not, then we call them the uneven cash flows. So let's study the annuities first. We are looking at two types of annuities, the ordinary annuities and annuity dues. Ordinary annuity is a series of equal payment made at the end of each period. For example, the first payment made at the end of the first year, second payment at the end of the second year. While annuity due is a series of equal payments made at the beginning of each period. So first payment will be made at the beginning of the first year, which is now, and second payment will be made at the beginning of the second year, which is pretty much the end of the first year. So if we look at example of the ordinary annuity, we are looking at interest payment from bond issuers. Usually they are paid semi-annually, so the first payment will be in 6 months, second payment will be 12 months later. And an example of an annuity due, in many lease arrangements, the first payment is due immediately and each other payment must be made at the beginning of the month. So if we look at the timeline again, the timeline illustrates the idea of ordinary annuity and annuity dues. So ordinary annuity, you see the payment is made at the end of each time, each period, and for annuity due, the first payment is made at the beginning of the first year, and second payment is made at the beginning of the second year. So you can think of annuity due as the whole ordinary annuity moving ahead for one period, right? So you're moving the whole package 1 year ahead. For the future value of ordinary annuity, let's take a look at this example. What is the future value of this 3-year ordinary annuity? Well, each payment is $100 when the interest rate is 10%. The key is to find out the future value of every cash flow involved and then sum them up. So when we look at the first one will compound for 2 years till the end of third year. So 100 will become 121 by the end of year 3. And second payment, since it's received at the end of the second year, you will have 1 year to compound. So this 100 will become 110. You understand it's 100 multiplied by 1 plus 10% at the power of 1, right? And this last payment will have no time to compound, so it will remain its face value. And we sum them up, 100 plus 110 plus 121, we will get the total future value as 331. And that is the total future value of this 3-year annuity, 3-year ordinary annuity. We can use the formula for the future value of the ordinary annuity. It is payment multiplied by 1 plus I at the power of n minus 1 and then divided by the interest rate. So if we plug in the numbers into this formula, $100 payment multiplied by 1 plus 10% at the power of 3 minus 1 and then divided by the 10% interest rate. So we will have the same result as 331. So you can take this formula as a shortcut of doing this step by step and summing them up. If we use the financial calculator, we are still looking at these 5 buttons. We tell the calculator 3 as n, 10% interest rate, so 10 as IY, and now we use 100 as payment because we do have 3 payment, each payment being 100, and then we put 0 as PV and we compute for the future value. So we have 3 payments, each payment being $100, but other than that we do not have any other lump sum present value at the beginning, so we enter 0 for the present value to calculate the future value of this 3-year annuity. To calculate the future value of an ordinary annuity according to Excel, we try equals to future value, and again, just like what you did with the single cash flows, we tell the Excel that 10% is the interest rate. We do have 3 payments now, each payment is $100, and we are using 0 as present value now, and 331. So, well, if we use 10%, 3 years, but a negative 100 as payments, then we will have a positive future value result. But either way, the amount are the same, so we just know again the negative positive sign is just a way to differentiate the direction of the cash flows. If we want to solve for the present value, the idea is actually consistent with the idea of calculating the future value. So we are looking at the present value of every cash flows, and we sum them up. So for example, 82.64, how do we get this number? We're actually using 100 divided by 1 plus 10% at the power of 2, because there are 2 years in between from today till the end of the second year. And 75.13 is 100 divided by 1 plus 10% at the power of 3. And we sum all these numbers up, we get 248.69 total present value of this 3-year ordinary annuity. Formula goes like this: payment multiplied by 1 divided by I, and then minus 1 divided by I multiplied by 1 plus I at the power of n. So plug in the numbers into this formula, you can get the same result, 248.69. I think it will be much easier or faster if you use a financial calculator. So now you are telling the calculator, same $100 as payment, 3 years, 10%. Now calculate the present value. You will put the future value as 0. To calculate the present value of this ordinary annuity, we say equals to present value and then 10% interest rate, 3 payments, each payment being 100, and no future value, 248.69. You can also put the $100 as payment, then you will get a positive number for the present value, but the amount will still be 248.69. Now, what about annuity due? So far we talked about the calculation of the present value and future value for ordinary annuity. You notice that annuity due is like moving this whole ordinary annuity 1 year ahead. So from the end of the first year to the beginning of the first year, end of the second year to the beginning of the second year, right? So this gives you the idea that the present value of the annuity due is the present value of the matching ordinary annuity multiplied by 1 plus I, which is the interest rates. So 248.69 is the present value of the 3-year ordinary annuity. Then if you multiply by 1 plus 10%, you get 273.56, and that is the present value of this annuity due. Same idea applies to the future value calculation for annuity due. So we use the future value of the ordinary annuity multiplied by 1 plus I, and then we get 364. That's the future value of this 3-year annuity due, while each payment is $100. We can also use the financial calculator to get the future value and present value of the annuity due directly. The key is to switch your calculator to the BGM mode. I do have the video on D2L that demonstrate how to switch from end mode to beginning mode, and if you want you can switch back from beginning mode to the end mode. So check out that video and follow the instructions and set your calculator under the beginning mode. And then once you are at the beginning mode, then input the same inputs as what you did with the ordinary annuity, but then as you see your results will be different. Now your present value will be 273 and your future value will be 364. This is consistent with your result over here. What do we do with Excel? If we want to find the present value and future value of the annuity due, we just need to tell Excel that we are looking for results for annuity dues. So for the present value, we use the same PV function and same 10% interest rate, same 3 years, same $100, 0 future value. And now notice that type. So type equals to 0, or say by default is for ordinary annuity. But if we put 1 as type, then we are looking at annuity dues. So then we are looking at present value of this annuity due, 273.55. For the future value, same idea. Same 10%, same 3 years, same $100, 0 PV, but type will be 1. For the annuity due, then 364.10. So far we talk about annuities which have equal amount of payments all the time, and we talk about how to calculate the future value and present value of both ordinary annuities and annuity dues. So what if the cash flow amounts actually are not the same all the time? Then we are looking at the so-called uneven cash flows. So for the uneven cash flows, the idea is still the same if we are looking at, for example here, 4 different amount of cash flows. To calculate the total present value, we calculate the present value of every one by one. We sum them up, and we get, in this case, 530.08. So for example, how do we get 225.39? It is the $300 at the end of year 3 divided by 1 plus I at the power of 3. And the negative 34.15 is the negative 50 divided by 1 plus I at the power of 4. So you calculate one by one, sum them up, get the total present value. Now with the financial calculator, again, I do have a video on D2L that explains how to calculate NPV, which is the total present value of a series of uneven cash flows. So check out the video demonstration and try to follow step by step till you get the right results. In this example, in the VA2 Plus calculator, what you need to input is the CFO is 0, CF1 100, CF2 300. So this is according to the timeline. Cash flow at the end of year 1, year 2, year 3, and year 4. Then you input 10 as IY and then press NPV button to get NPV. Now maybe this sounds a little bit confusing to you, but again, check out the video demonstration posted on D2L. You will have a much better idea. What do we do with Excel for this? If we have a series of unequal amount of cash flows, so I'm just listing all these different amount of cash flows here, and I'm trying to find the total present value. So I'm using the NPV functions, and I tell the calculator that discount rate is 10%, and then all I need to do is to include all these cash flows. That's it. Pretty simple, right? So by now you should be able to calculate present value and future value for single cash flows, multiple cash flows, including annuities and uneven cash flows. Now we'll discuss some special issues in time value of money, and we'll start with the concept of the so-called effective annual rate. What is effective annual rate? This is the annual interest rate when compounding occurs more than once a year. So let's assume a bank offers 6% annual interest rate for deposits, and this is stated in the contract, and so we call it either nominal interest rate or sometimes quoted interest rate, and I'm using I norm for nominal interest rate. Now if the bank specifies that they use monthly compounding, that means the interest will be compounded on a monthly basis, so every month. That also means 12 times a year. Then we will actually have an interest rate of 0.5% per month, and that 0.5% is the 6% annual interest rate divided by 12 months in the year, and that is the interest rate each period. So will the future value of a lump sum be larger or smaller if we compound more often? If the stated, or say the nominal quoted interest rate is constant? Actually, the answer is the amount will be larger. If compounding is more frequent, then interest is earned on interest more often, and then the future value result will be bigger. Suppose we can compound m times a year. So m would be 12 if we are doing monthly compounding, m would be 365 if we are doing daily compounding, right? So future value will be present value multiplied by 1 plus this interest rate each period. So future value will be present value multiplied by 1 plus this interest rate each period, and then compound for these many times. And so m multiplied by n, that is how many times in n years, right? So for example, if we are doing 12 times a year but for 5 years, then a total 60 times of compounding instead of just 5 times. So let's see, if we are looking at a 12% nominal interest rate, semi-annual compounding for 5 years. Semi-annual means twice a year, so each 6 months we're actually using 6% instead of 12%. So we're using 6% to compound, and within 5 years we'll compound for 10 times. So we are actually using 100 multiplied by 1 plus 6% at the power of 10, we get 179.08, and that is the future value after semi-annual compounding. If we are looking at different compounding frequency, we will realize that future value will be different, depends on the compounding frequency. So within the same 5 years, if we're doing annual compounding, we end up with 176. If we're doing monthly compounding, then we're using 1% per month for 60 months, then we will end up with 181. If we're using daily compounding, then we're using this daily interest rate, then compound for these many days in 5 years, and then we end up with 182. So the idea is, the more frequent compounding you have, then the higher future value you will end up with. And this also gives you the idea that the more frequent compounding you have, then the actual effective annual interest rate will be higher. So let's see, if we are looking at semi-annual compounding, we invest $1 and 12% annual interest rate under the semi-annual compounding, you understand why $1 will become 1.1236 instead of only $1.12, right? So in this case, the effective annual rate is not 12% anymore, but 12.36%, because the $1 invested for 1 year at semi-annual compounding would grow to the same value of $1 invested for 1 year at 12.36% annual compounding. So the idea of effective annual rate is to find out the actual, or say effective rate of return you can have based on frequent compounding. So the formula for this effective annual rate is actually pretty simple. It's 1 plus the nominal annual interest rate divided by the number of compounding frequency in a year, and then compound for m times within a year, and then minus 1. So in the semi-annual compounding case, this gives us 12.36%. You can also plug in the numbers for quarterly compounding, which is 4 times a year, monthly compounding, which is 12 times a year, or daily compounding, which is 365 times a year, and you can verify these numbers, and the pattern suggests that higher frequent compounding, then higher effective annual rate we can have. So we can use this to compare investment. In this example, you are offered a note that pays $1,000 in 15 months, or say for 56 days for $850. So you will pay $850 now, and in 15 months or for 56 days you will receive $1,000. You currently do have $850 in the bank that pays 6.76649% nominal interest rate with 365 daily compounding. And if you use this number divided by 365, that gives you a daily interest rate of this much, which gives you an effective rate of 7.0%. So you have a choice now. You can either leave the money in the bank enjoying the 7.0% effective annual rate, or you can pay $850 to buy this note that will give you $1,000 in 15 months. So the question is, should you buy it? We can try different ways. We can compare the two investment opportunity and see which one give us higher future value. We can also try to calculate the present value, or we can actually compare the effective annual rate between the two investment opportunities. If we calculate the future value, if we leave the $850 in the bank, then based on the daily interest rate for 456 days, we will have 924.97 in the bank, and this is lower than what the note offers, so then we will buy the note. Right, so this is to calculate the future value based on daily compounding and compare how much we can get under each different investment opportunities. Or we can say, what if we look at the note offer and see what is the present value of this? If we know we will get $1,000 in 456 days, and we are using the daily interest rate offered by the bank to discount this $1,000 promised by the note, then we understand the present value of this investment opportunity, or say this note opportunity, is $918. Since we only need to pay $850 to buy this note, which does have a present value of $918, that means we are getting a good deal. So let's pay $850 and buy the note. Or we can compare the rate of return. Remember, the bank offers a 7.0 effective annual rate. And what about the bank? What about the note? So if we are looking at for 56 days, and we are looking at a present value of $850, that's how much we have to pay for the note, and a future value of $1,000, which is how much we can receive based on what the note promises. Then every day our daily interest rate is this much, and we can also calculate the effective annual rate based on the daily rate. So we're using 1 plus the daily rate, compound for 365 days in a year, minus 1, we get 13.89% from this note, and that is much higher than the 7% effective annual rate that the bank pays. So no matter whether you are looking at the future value, the present value, or the rate of return, it looks like the note is a better deal than just leaving your money in the bank. Here, let me show you a shortcut to calculate the effective annual rate using your financial calculator. So you just input 365 as CY into your calculator, and your nominal interest rate actually will be the daily interest rate simply multiplied by 365. So this is the nominal annual rate. Then you can compute for the effective annual rate, 13.89%. If this sounds a little bit confusing to you, go check out the video I posted on D2VL that explains how to calculate effective annual rate. Again, it is a very detailed step-by-step demonstration. You will master this smoothly after you watch the video.